So now we are starting chapter 15, applications of aqueous equilibria. The first section is the common ion effect, and in fact we've actually already done this. An example would be where you have a weak acid and the conjugate weak base both present in a solution. The common ion here would be F minus, because HF, when you have the reaction, one of the products is F minus. Here you have F minus, so they both have F minus in common. We've already done those problems, so we're not going to do any new ones right now. Section 15.2. Buffered solutions. We've done these as well. We just didn't use this fancy word buffer. Some of the AP questions had the word buffer in there, and some of you got a little confused, but it was okay. You didn't need to know that we were working on buffers yet, and now you do. So first, the definition. A buffer solution is a solution that resists changes to pH and contains a weak acid and a weak base. So even if you have a strong base or a strong acid, you add those to your buffer, the pH does not change by much. When a strong acid is added, the pH doesn't change because the weak base that's in the buffer will react with the strong acid, just like this. So the weak base reacts with your strong acid, and you produce the weak acid. That neutralizes and gets rid of the protons, the H+. Likewise, if you had a strong base, again the pH doesn't change much because the weak acid in the buffer reacts with a strong base according to this. So here's your strong base, hydroxide, reacts with your weak acid, you produce water and your conjugate weak base. So we've gotten rid of our strong hydroxide. Okay. And we've already been doing these problems, lots of them. We just didn't call the problems buffer problems. So let's do one. Just to remind you, we've already done this, but we'll do another one. And if you want to pause this and do it on your own, that is your prerogative. We're going to set up an icebox. Whoops. That's okay. Nothing broke. Okay, so first we need to figure out who's going to react with whom. We've got strong acid, weak base, weak acid. Well, the strong acid, we're just going to call it H+, is going to react with the weak base. You have to recognize you've got a strong acid and a weak base. Acids and bases are on the same side when you have a strong and a weak. And this goes to completion and you form NH4+. Notice this right here, we don't care about the Cl-, all we care about is the NH4+. We're going to set up an ICF box. So we have to figure out our concentration. We put 0.1 moles into 1 liter, which would make a 0.1 molar solution. So that's 0.1 molar. NH3, we didn't do any dilutions here because we didn't add any volumes together. The NH3 is 0.25 molar, that was given to us. And the NH4+ right here is 0.40 molar. Check for your limiting reactant. You should recognize that this is limiting right here. So down by 0.1, down by 0.1, up by 0.1, 0, 0.15, 0.50. Those are molarities. Now I need to put this into an icebox. For my icebox, I need an acid, weak base reaction. Notice I have both my NH3, my weak base, and my NH4, my weak acid, present. I was given a Kb, so I want to use a base reaction. So I will have NH3 plus water. That's whenever you have a Kb, you'll always use your weak base plus water, and we'll make the conjugate weak acid and hydroxide. We just showed that NH3, ammonia, is going to form hydroxide. That's why it's a weak base, because it forms hydroxide in solution. And we use our initial concentration from the ICF box. So the NH3 was 0.15, The NH4 plus was 0.50. This is 0. We don't worry about water. .5 plus x and x. Now we just plug this into our Kb equation. Kb is products over reactants, 0.5 plus x times x over 0.15 minus x. We assume x is much less than 0.15, and that allows us to cancel out the plus x and the minus x. And I solve for x. I get x is equal to Kb. Where's my Kb? It's right here. 1.8 times 10 to the minus 5 times 0.15 divided by 0.5. And x comes out to be 5.4 times 10 to the minus 6. Now we have to check, what did the question ask us? What did I just find? Note that x is OH minus, not H plus. You have to always check. What are they asking for? What is this x that I've even solved for? So I've got all this writing all over the place. I want to find the pH. We got to reread. We got to make sure we read very carefully. So I now know that OH minus is 5.4 times 10 to minus 6 molar. So my POH is negative log of that, which is 5.27. And so my pH is 14 minus 5.27, which is 8.73. And that's the final answer for that one. Okay. Moving on. Section 15.3, buffering capacity and more other types of problems. We'll fix that. And other types of buffer problems. Okay. So first, what is this buffering capacity stuff? Here's your definition. The capacity of the buffer, or buffering capacity, that's how much hydroxide or H plus protons that you can add to a buffer without causing a large pH change. So the more moles you have of the weak acid or weak base, the larger the buffering capacity. All right, here's a problem. Which buffer has a larger buffering capacity? One that is 1 molar ammonia and 1 molar ammonium chloride, or one that is 0.5 molar ammonia and 0.5 molar ammonium chloride? This should be kind of obvious. It's the one with the higher concentration. That would be our answer right there. Okay, moving on. New problem. How to prepare a buffer. A chemist needs a solution buffered at pH 4.3 and can choose from the following acids and their sodium salts. So, oh wait, I've already told you how to do it. Okay, so here are our 4 acids, and we want to figure out which one of these should we use. So, oh, actually this is part of the problem. Find out for each of these what would the ratio of the weak acid to weak base be in order to achieve the pH of 4.3, and then which acid would be best to use. So for each of these 4, we're going to calculate this ratio. So you want to think about, what do I know? I know my Ka for each one. I just want the ratio of HA to A minus, and I know my pH. If you know pH, you know H plus, and if you know how to do this, go ahead and do it. I'm about to tell you how to solve it, so you can pause right now if you think you have an idea. Okay, we know the pH, so we can get H plus, the concentration of hydronium ion, or H plus. There you go, there it is. Now we're going to plug this into the equation. We know H3O plus, we know the Ka, we know this equation for Ka. Here's our ratio right here. We play around with our equation to get our ratio, and it's just H plus over the Ka. You could solve for each of these. I'm about to give you the answer for each of them. Here's the 4 answers you get. So for solution A, the ratio of acid to base, weak acid to weak base, would be 0.037 up to part D, letter D, would be 1400. Now, which acid would be best to use? Well, you want the biggest buffering capacity possible, but you want your ratio of acid to base to be approximately 1. You want about the same amount of HA to A minus. Well, the one with the closest ratio to 1 right here is C. So we would pick benzoic acid, C. And you want the ratio close to 1 because you want as much weak acid as weak base. You don't want a huge amount of weak acid and very little weak base. That would not be a good buffer. All right, on to section 15.4, titrations and pH curve. We did this in class a little bit. First, what is a titration curve? It is a plot of pH versus volume of titrant added. Here's some examples. So here's our first example. We've actually got two titration curves on a single graph here. So pH is on the Y scale. Volume of titrant added is on the x-axis. And some notable characteristics. You've actually seen these. They should be in your notes from today already. The strong acid titration starts at approximately 1 for the pH. The weak acid starts at around 3. And then at the equivalence point, that's where you have this sudden huge rise. And it's halfway, if you look at the big rise, and you go halfway from the bottom to the top, the midpoint right there, that's equivalence. So equivalence happens right at about 30 mils for both of these. The volume, if you have the same concentration of weak acid or strong acid, then the equivalence point occurs at the same point if you're using the same base for the titration. It doesn't matter if your acid is weak or strong, your equivalence point occurs at the same volume if your concentrations start out the same. Okay, so strong acid, equivalence point right here, pH is 7. The weak acid, halfway from here to the top, you'll notice the equivalence point is about right here, halfway from the top to the bottom, and it's around 9. Notice our pH at equivalence, if you have a weak acid titrated with a strong base, will always be greater than 7. It's because at the equivalence point, all of the weak acid and the strong base are gone. All you have left is a weak base. Last thing, if you go to half the equivalence volume, so here, equivalence is at 30. If you go to half of that at 15 right here, you go up to this curve right here and you go over to the side. Your pH equals your pKa of the weak acid. So pH is about 5. pKa would be 5. Ka would be 10 to the minus 5 for this weak acid. All right, now these are bases being titrated with a strong acid. Can you figure out which of these is the weak base and which is the strong base? You want to think to yourself, will the weak base have a lower pH or a higher pH? I'm going to mark it on here, but you try to figure it out yourselves. You can pause if you want to. And this top one would be our strong base, titrated with a strong acid. Over here would be our weak base, titrated with our strong acid. Okay. So the curve, it's like a reverse, upside down titration curve of the acid being titrated with the base. Okay, some notable characteristics. The strong base, notice we start up at 13 because it's a strong base. The weak base starts at around 11. We have this concavity difference between the weak. It starts concave up, goes concave down. The strong is just concave down all the way up to the equivalence point. Now the strong base titrated with a strong acid. We're going to look at the top and the bottom, go halfway right there, and pH 7, still pH 7 at equivalence when you have strong and strong. Okay, weak base, strong acid. So we go halfway from the top to the bottom. It's right here. And at that equivalence point, the pH is about 5.5, give or take, which is less than 7. And that's because if you have a weak base and a strong acid at equivalence, the strong acid is gone, the weak base is all gone. All you have left is the conjugate weak acid. And if all you have is a weak acid, your pH is going to be acidic or less than 7. Now, the pKa or pKb again. Let's look at that. So, we look at our equivalence point, 50 milliliters. We go to our half equivalence point, 25 milliliters. You go up to here. You go over to this side, 9. So, that tells us the pH is 9, but it's the pOH will be the pKb. So if the pH is 9, the pOH will be 5, right? Has to add up to 14. pOH will be 5. The pKb is 5. The Kb would be 10 to the minus 5 for this titration curve. Oops. Okay. Identify the Ka for the weak acid in the titration curve on the previous page and the Kb for the weak base in the titration curve above. I just did that with you. You can go back and listen to it again. I'm going to give you the answers right now. Actually, I need to look at it because I forgot what the answer was for the other one. So for the weak acid, let's see, you go to the half equivalence point. You should pause if you want to do this on your own. Go to the half equivalence point. We're at 5. All right, so pH was 5. Number 1, the pKa is 5, so the Ka is 10 to the minus 5. It's approximately. It should say approximately. For number 2, again, pause this if you want to try to do it on your own. Okay, go to the half equivalence point, 25 mils. Go up to the curve and over to the side. Wah! Not very straight there. So the pH is 9. The pOH is 5, which is the pKb. So the Kb will be approximately, same thing, 10 to the minus 5. Interesting. Okay, 2 totally different curves gave us similar Kas and Kbs. These could not be, actually, could these be a conjugate acid-base pair? Remember, Ka times Kb has to equal 10 to the minus 14. Well, this Ka times Kb is only 10 to the minus 10. So could there be a conjugate pair for these 2 titrations? Absolutely not. Hopefully you got that. Okay, new problem. Calculate the pH at the equivalence point when 50 milliliters of 0.1 molar acetic acid, Ka given, is titrated with 0.1 molar NaOH. Okay, first, you got to find the volume of NaOH needed to reach the equivalence point. If you're ever asked to find the pH at equivalence, you better find out the equivalence point first. You need your volumes. So, we have our reaction. You just do stoichiometry. So, by stoichiometry, we know we have 0.05 liters and 0.1 moles per liter of the acid. I'm just going to call it HA. I don't want to write out the whole formula. And it's a 1-to-1 ratio, so 1 HA to 1 OH minus, it's not 10, it's a 1. And I have 0.1 molar NaOH. So for 1 mole, 0.1 molar, 0.1 moles OH minus, I have 1 liter. And then I see that that is equal to 50 milliliters. Because the 0.1s cancel, the 1s cancel, liters cancel, everything cancels. 0.05 liters is 50 mils. Okay. So I know I need 50 mils. Notice I'm going to be adding 50 milliliters of my NaOH solution to 50 mils of my acetic acid. I have to figure out my reaction. It's actually right here. I don't have to figure it out. I already did. I do an icebox. here we go. Initial concentrations, why is this 0.5? It's not 0.5, it's 0.05. Okay, fix that real quick. So our initial concentrations got diluted by a factor of 2 because I have 50 milliliters of the acid, 50 milliliters of the base. They both started at 0.1. They're diluted by a factor of 2 because these are equal volumes. So my initial concentrations are 0.05. I see they're both limiting. That's the definition of equivalence point. Both chemicals will be limiting. So they both go down by 0.05. The acetate has to go up by 0.05. The weak acid and the strong base end up at 0 at the equivalence point as definition of the equivalence point. These are gone. And all I'm left with is my weak base, which is why my pH hopefully will end up being acidic. Basic. Sorry, all I have is the weak base. Okay, now I have to set up an icebox with the concentrations from this final row. This was an ICF. So we take the F row and we have to set up an icebox. We only have the weak base present, so I need to do a reaction with the weak base. And since I'm going to have only the weak base, I need a Kb. So first I've got to calculate the Kb. Remember, Ka times Kb is 10 to the minus 14. So here's my Kb. And here's my reaction, my weak base. I've got to come up with a whole new reaction. Weak base and water. We always make hydroxide, and one of the H's from water transfers over to the weak base to get acetic acid. Okay, we have to set up our icebox. ICE, icebox. And we see in our icebox, ICF, ICE, that I use my initial concentration from my final row. That's where that came from. Now this just looks like a regular old typical icebox. And I find X. We have to assume X is really small. I use my Kb equation, X times X over 0.05 minus X, but X I assume is really small, equals my Kb that I calculated. I solve for X. Now note that this is hydroxide, not H+. Always important to check these things. So I can get my POH from my OH, my hydroxide right here. Here's my POH, which gets me my pH, which is what I was looking for, and I'm done with that problem. Last topic du jour. That means of the day. Acid-base indicators. So an indicator, what is an indicator? It's a chemical that indicates the end point of a titration. So we've reached the end point, and there's some chemical that's going to indicate it. That chemical changes color. And you want the end point and the equivalence point to be at the same exact point. So you pick an indicator whose color changes at the pH of equivalence. And to get that to be true, you want your indicator's pKa. Indicators have their own pKa's. You want the indicator's pKa equal to the equivalence pH. Not to be confused with the half equivalence point, because that's a totally different pH. This is the equivalent point's pH should equal the pKa of the indicator. Remember, the half equivalence point is the pKa of the weak acid. So it gets confusing because there's so many terms in here. So here's some examples of indicators and some pKa's. So we can look, for example, methyl violet is purple all the way down to pH approximately 1.5, and it's yellow down at 0, and it's sort of greenish right around pH 1. Thymol blue, pink at low pH, yellow at middle pHs, purple at high pHs. So just a whole bunch of different pH indicators, and the pH at which here's the pH at which they change color. Here's another table of pKa values of indicators and the useful ranges for where they are useful. Okay, so which indicator would be best for a strong acid, strong base titration? Let's go back and look what we know about strong acid, strong base titrations. The pH is 7 at equivalence. Now if you can figure this out on your own, pause this, Look at your notes, figure it out. You want a pKa to be about 7, because the equivalence point for a strong acid, strong base is 7. So you want an indicator whose pKa is 7, and that would be bromethymol blue. Bromethymol blue, because its pKa is 7. Okay, so which indicator would be best for the weak acid titrated with a strong base on page 2? Pause this if you want to figure this out on your own. I'm going over to page 2, looking at my titration. All right, equivalence right here. And my pH at equivalence is right here. And I'd say it's about 9, between 8 and 9. So I look for an indicator whose pKa is approximately 9. Oh, it's between 8.5 or 9. You know, both phenol red and phenolphthalein could work. I would pick the phenolphthalein because I was saying it was between 8.5 and 9. So personally, I'd pick the phenolphthalein. Phenolphthalein. I hate spelling that word. PHTH. It's very confusing. Phenolphthalein, because its pKa is 9.3. The equivalence point pH was approximately 9, and those are pretty close. Okay, what about the weak base, strong acid titration on the previous page? Here we go. Okay, here's our equivalence points. It's nicely marked for us. And the pH at the equivalence point, it's about 5.5. It's between 5 and 6. So let's look. Oh, look, right there, 5.1. That's a nice pKa if you want your equivalence point, if you know your equivalence point is at between 5 and 6. So for this one, we would pick methyl red. Methyl red. My spelling, my handwriting is just awful. Okay, that is it. This is what you need to do for homework after watching this recording. Okay, have a great evening.